Welcome to this lecture on time series analysis. Today we are diving into the ratio to trend method. If you have ever wondered how businesses separate their underlying growth from predictable seasonal spikes, like selling more ice cream in summer, this is exactly how they do it. Let us get started. Before we can isolate the seasonal pattern, we must understand the forces shaping our data. Why does this matter? Because real world data is messy and we need a structured way to break it apart. The ratio to trend method relies on the multiplicative model. This model assumes that any single data point is the result of multiplying four distinct forces together: the long term trend, the repeating seasonal pattern, long term economic cycles, and random unpredictable events. By assuming these forces multiply rather than add, we acknowledge that seasonal swings grow proportionally larger as the overall trend grows. Let us look at where this method mathematically begins. The formula on your screen represents the classic multiplicative model. Y is the actual observed data point, like monthly sales. T is the trend, showing long-term growth or decline. S is the seasonal component, the short-term repeating cycle. C represents long-term business cycles, and I stands for irregular, random noise. If the trend increases, the actual value y increases proportionally because they're all multiplied together. To isolate the season, we assume the cyclical component is stable and irregular noise averages out, simplifying our focus to just the trend and the season. Now that we have simplified our model to just trend and season, how do we actually extract the seasonal effect? We do this by reversing the multiplication. We take the actual observed data, y, and divide it by the expected baseline trend, t. This division effectively strips away the long-term growth. To make the result intuitive, we multiply by 100 to express it as a percentage. This gives us R, the ratio to trend. If the actual data perfectly matches the trend, the ratio is exactly 100%. If the actual data is higher, the percentage increases, indicating a positive seasonal boost. Let us visualize exactly what this mathematical division looks like on a graph. On the screen, you see a plot of sales volume over time. The straight dashed line represents the mathematical trend we calculated. This is what the data would look like if seasons did not exist. The wavy solid blue line is the actual reality we observed, peaking and dipping. By measuring the vertical gap between the reality and the trend line at any given point and expressing that gap as a percentage, we capture the pure seasonal effect for that specific moment in time. Let us put this formula into practice with a concrete example. Suppose we are analyzing quarterly sales. We are given that the actual sales volume for the first quarter, Y, is 15 units. We are also given the mathematical equation for the trend line, which is T equals 10 plus 2 times T, where T is the time period. Our first goal is to find the expected baseline trend for quarter 1. We do this by substituting T equals 1 into our trend equation. This will tell us exactly where the straight trend line sits on the graph during this specific quarter. Continuing with our calculation, multiplying 2 by 1 and adding 10 gives us an expected trend value of 12. This means we expected to sell 12 units based purely on long-term growth. But reality gave us 15 units. To find the seasonal percentage, we divide the actual 15 by the expected 12 and multiply by 100. The result is 125. Physically, this means the first quarter brings a 25% seasonal boost above the normal trend. We would repeat this for every quarter to build a complete seasonal profile. Once we calculate the ratios for every single quarter across many years, we average them to remove random noise. However, this brings up a new challenge. For quarterly data, a perfect seasonal cycle should average out to exactly 100 per quarter. This means the 4 quarterly indices must sum to exactly 400. If our calculated averages sum to something else, like 410, our indices are slightly inflated. We cannot just leave them like this because they would accidentally alter the overall annual trend. We must adjust them so they sum perfectly to our theoretical baseline. To fix inflated or deflated seasonal averages, we calculate an adjustment factor, denoted by the letter K. Where does this come from? It is simply the ratio of what we want over what we actually have. The numerator is 400, which is the ideal theoretical sum for 4 quarters. The denominator is the actual sum of our unadjusted averages, which in our example is 410. By dividing the ideal sum by the actual sum, we find the exact proportion by which every single quarter must be scaled. If the actual sum was too low, this factor would scale the numbers up. Let us see how this adjustment factor is applied. We are given an unadjusted average for the first quarter of 110. We also know our adjustment factor is approximately 0.9756. Why do we multiply them? Because every unadjusted average is currently about 2.4% too high. By multiplying the unadjusted first quarter by our adjustment factor, we scale the value down slightly. The final adjusted seasonal index is approximately 107.3. This definitive number guarantees that our seasonal adjustments do not distort the overall annual trend. We have focused heavily on the multiplicative model. But what if the data behaves differently? Sometimes seasonal swings do not grow proportionally larger as the company grows. Instead, they remain constant in absolute size. For example, a shop might sell exactly 50 extra ice creams every summer, regardless of whether their baseline sales are 100 or 1000. When a time series behaves this way, we use an additive model. In this scenario, the components are added together rather than multiplied. This requires a parallel technique to isolate the seasonal component, known as the difference from trend method. Here is the mathematical translation of the additive concept. Because the components are added together, we isolate the seasonal component by subtracting the trend from the actual data, rather than dividing. S equals Y minus T. Y is the actual observed data and T is the expected trend. If the actual sales are 150 and the trend is 100, the seasonal effect is simply positive 50 units. This method isolates the pure seasonal addition or subtraction, giving us an absolute number rather than a percentage. It is a direct parallel to the ratio to trend method. No statistical method is perfect, and the ratio to trend method has a critical vulnerability. Its accuracy depends entirely on how well the underlying trend line was fitted to the data. Why is this so dangerous? Because every single seasonal calculation involves dividing by the trend value. If you force a straight line through data that is actually curving upward exponentially, your calculated trend values at the ends of the graph will be far too low. When you divide the actual data by these artificially low values, your seasonal ratios will look massive, creating a false illusion of extreme seasonality. It is highly instructive to compare this method with its close cousin, the ratio to moving averages method. Both aim to isolate the season by dividing actual data by a baseline trend, but they calculate that baseline entirely differently. The moving averages method computes a rolling average, which naturally bends to follow the true shape of the data. However, this causes you to lose data points at the very beginning and end of your series. In contrast, the ratio to trend method uses a fitted mathematical equation, meaning no data is lost. It is preferable when long-term growth is highly predictable. We have covered a lot of ground today. Let us review the key takeaways. First, the ratio to trend method isolates seasonal patterns by dividing actual observed data by a mathematically fitted baseline trend. This relies on the multiplicative model, stripping away long-term growth to expose the repeating seasonal heartbeat as a percentage. Second, we learned that these raw percentages must be adjusted so they sum perfectly to a theoretical baseline. ensuring the overall trend is not distorted. Finally, always remember that this method blindly trusts the trend equation you provide, so an accurate trend line is absolutely essential.